more or less, we covered the basics of OLS model, ordinary least square model. And all of us are familiar with the 5 assumptions. Expectation of UI is equal to 0. Variance of UI are constant. Covariance between UI and UJ, that is equal to 0. Non-stochasticity of Xi, which results in covariance between Xi UI is equal to 0. However, non-stochasticity of Xi is only the sufficient condition to ensure covariance between Xi and UI to be equal to 0. So Xi may be stochastic as well. However, we need to maintain the condition that covariance between Xi UI should be equal to 0. And 5th assumption is regarding the distributional aspect of the error term, that is the normality assumption. UI is independently and normally distributed with expectation of UI is equal to 0 and variance of UI are constant. Okay, so within this time, and you revised the entire thing, most of you revised the entire thing thoroughly. Some students could not get time to revise the entire thing. However, more or less, you are familiar with all of these assumptions. Now, among these assumptions, expectation of UI is equal to 0. It is a consistency requirement. There are positive discrepancies, negative discrepancies when we are plotting the scatters, and then we are fitting a line, so naturally, if the error is random, the number of positive discrepancies will be more or less similar to that of negative discrepancies, so that will adjust each other, and on an average, expectation of UI will be equal to 0. So this is not a stringent assumption, rather it is a consistency requirement. However, the second and third assumptions, that is variance of UI are constant and covariance between UI UJ that is equal to 0. These are very specific assumptions. Let's first handle with the first thing, that is expectation of UI square or variance of UI that is equal to a constant. So as I mentioned earlier too, if I consider income class, there are several layers. Now, if I consider different countries, all countries have different socio-economic cultural traits. So all these things, suggest that whenever we will consider the data of a single variable, or collect the data of a single variable, or collect the data of 2 variables and try to establish a relationship between the two, there will be, differences in the analysis, differences in the patterns. If I consider different income class, and the easiest example, if I consider the MPC, across income class it will vary. Now, if I consider different countries, naturally, depending on the culture, depending on socio-economic, demographic situations, MPC will vary. Okay. So starting from the regional analysis, if I move towards state-based analysis, if I move towards country-based analysis, etc., we will find that, the pattern of beta that varies, or pattern of the random error or variability of the random error, span of variability of the random error, that cannot remain constant. It will vary across different groups, across different classes, etc. Okay, so homoscedasticity assumption or homogeneous variance assumption, it is not a general assumption. It is not a consistency requirement. To make the model classic or to have a classical analysis, we are assuming to begin with this variance is constant. However, when we will go for the real life data, under many circumstances, we will find that error variance is varying when we are moving from one group to other. Now, heteroscedasticity, that is variability of error variance, that is more common in cross-section analysis rather than time series analysis, okay? Because when we are talking about different regions, different countries, different states, so we are changing or differing the cross-sections, different households. So, mostly the examples I'm giving, these are based on cross-section analysis. It is not that in the time series analysis there will be no heteroscedasticity. However, it is more common in the cross-section analysis. Okay. So what we have to do, we have to learn what is meant by heteroscedasticity. What will be the consequences to our OLS measure, ordinary least square measure, which we already estimated, which we already learned, if there is heteroscedasticity in the model? Okay, what will be the consequences? Whether the estimators will still remain unbiased, minimum variance estimator, or blue property will be maintained or not. Okay, so what are the consequences? Number two, how we will detect heteroscedasticity. And number three, if we find that OLS is not the right method to find the best linear unbiased estimator, is there any alternative way by which we can find out the best linear unbiased estimator? So what remains? Three questions we need to address. Consequences with respect to the standard OLS estimator. Number two, how we will detect the problem. Number three, if we find that OLS estimator is not giving us the best linear unbiased estimator, what will be the alternative technique which can provide us the best linear unbiased estimator? Okay, so three questions we need to address in presence of heteroscedasticity. After completing heteroscedasticity, the similar exercise we have to do in presence of autocorrelation. When we are considering the heteroscedasticity, that is, we are breaking the assumption of homoscedasticity, we are assuming that non-autocorrelation assumption still prevails. That is, all other assumptions remain intact. And when we will talk about autocorrelation, we will consider rest of the assumptions are same. Okay. And finally, we will mention something, if both the assumptions are not there, both the homoscedasticity and non-autocorrelation, then how we will treat it. However, that is more advanced thing, and it will be better to discuss this issue if somebody takes the special course. Okay. So we can discuss the matter in the special course. So in this semester, I'll stick to heteroscedasticity when rest of the assumptions prevail, and I'll consider the autocorrelation problem again when rest of the assumptions prevail. Okay, so this will be the sketch of our analysis. Today I'll give you a brief of heteroscedasticity, and then we will go through the matter, and then again we can discuss the things in next week. Is it visible?
Yes, ma'am.
Yes, ma'am.
Okay, so as I mentioned, in a linear regression model, we assume the error term has a normal distribution with mean 0 and variance sigma square. That is, we assume variance of UI is equal to sigma square, which we called the homoscedasticity assumption. But when the error term does not have constant variance, that is, variance of UI is sigma I square. That is, it is sigma 1 square, sigma 2 square. If I move from one individual to other, it is changing. Sigma 1 square, sigma 2 square, or from one household to another household, sigma 1 square, sigma 2 square. From one region to another region, sigma 1 square, sigma 2 square. Okay. Then from across the states, across the countries. So when I am moving from one observation to other, it is changing, it is varying. Okay, sigma 1 square, sigma 2 square, sigma 3 square, it is moving like this. Okay, so this is the idea. So, already this kind of diagram we discussed. During our viva or discussion, I asked this question to several students. At that moment, some people could answer, some people could not. This is the idea. So look at this three-dimensional graph. Along this axis we are measuring income, along this axis we are measuring saving. So in case of any macroeconomic savings income relationship, you do the things in this way. Along the horizontal axis you measure income, along the vertical axis you measure savings, consumption, etc. And this is the density or probability. Now this is the savings income line. As income is increasing, saving is also mildly increasing. If you consider consumption instead of savings, you will get the similar kind of graphs. Sometimes for the savings equation, we consider the negative intercept as well. So all these things happen. However, the curves are positively sloped in general. So in this case, the scatters, around this line, there are scatters. There are scatters around this line. And here I am considering three distributions. Actually, there are infinite number of distributions over this line because the scatters are around this entire line. So among these scatters, if I consider three distributions from the infinite number of distributions, we are getting the spread of all these distributions are equal. This is the assumption of homoscedasticity. However, here what I am getting, here the concentration towards mean is very high, tail is increasing. Here it is very flat type of curve, So the pattern of scatters around the line, that is variability of scatters around the line, or the difference or the distance of a scatter from the mean, that is changing. In case of variance, what we consider? Expectation of xi minus x bar or expectation of xi whole square. Okay. So difference of the observations from the mean, and then I consider square of that, take expectation, So here the distance of the scatter from the mean, that is varying. That is varying as we are moving along the line. Okay. So this is the presence of heteroscedasticity, non-homogeneous variability of the observations from the mean. And here, equal spread we are getting, equal spread of observation from the mean we are getting as we are walking along the line. Okay. So the left-hand side is the example of homoscedasticity, right-hand side is the example of heteroscedasticity. Now, if I consider a two-variable model, yi is equal to alpha 1 plus alpha 2 xi plus the error, the estimated value we got, for the regression coefficient, the slope coefficient, the gradient coefficient, that is capital Xi minus X bar into Yi minus Y bar divided by summation capital Xi minus X bar whole square, which in the deviation form can be written as summation small xi yi divided by summation xi square. And variance of that estimator, this slope coefficient is given by sigma square divided by summation capital Xi minus X bar whole square, or sigma square divided by summation small xi square. So I hope you can remember this formula because all of you went through this thing. Now, in presence of heteroscedasticity, if we apply OLS, the estimated value, the model looks alike. So if I consider the residual, then minimize residual sum of square, and then consider the first order conditions, we will get the same value. Okay, so the value of the estimator will not change. The value of the estimator will not change. However, if I calculate the variance of this estimator, we will find the variance will look like this. In fact, when we considered variance of the OLS estimator, we got summation xi square. In this place, we got sigma square. So as we got sigma square, a constant, we could keep it outside the range of sum. So one summation xi square will be cancelled and we will get sigma square by summation xi square. Here, I cannot bring that sigma I square outside the range of sum because it is a variable rather than a constant. Okay. However, we need to do the steps and we need to check how we are getting these variants. Okay. So to get this, we are considering a two variable regression model. From the very beginning, I'm considering the deviation form, because the steps will be simpler in that case. So I'm considering the deviation form. Okay, that is, I'm regressing xi minus x bar on yi minus y bar. Okay, so expectation of ui is equal to 0. Expectation of ui square, which is variance of ui, that I am considering sigma I square because I am considering heteroscedasticity. Covariance between ui uj, that is absolutely equal to 0 because I am considering autocorrelation. X, for simplicity, I am considering non-stochastic. Now for the estimation purpose and discussing the properties of estimator, I do not need the assumption about the distribution of error term. Therefore, I didn't write anything about the distributional aspect. That is, UI is normally distributed, etc. Okay. So I'm starting with beta hat OLS. The formula is this. Then I'm replacing yi by beta xi plus ui. Okay. So this is equal to beta plus summation xi ui divided by summation xi square. All of you know this thing because all of you presented all these things during your exam. So all of you could grasp all these things, So we are getting this. Once I get this, if I take expectation of beta hat OLS, it is expectation of this matter. So expectation of beta is equal to beta, a constant. And if I operate expectation with these ui, expectation will be operated with this ui. Since by the first assumption expectation of ui is equal to 0, this second term will vanish and we will get beta. So what we are finding that in presence of heteroscedasticity, the unbiasedness property is not disturbed. Still, the OLS estimator is unbiased. OLS estimator is still unbiased. Next, we calculate the variance of beta hat OLS, expectation of, or beta hat OLS is equal to beta plus this part. Beta hat OLS is equal to beta plus this part. So beta hat minus beta is equal to this part. So I'm using that. Again, all of you know this thing. So variance of beta hat OLS is equal to expectation of beta hat OLS minus beta, which is summation xi ui divided by summation xi square whole square of this. Okay. And as I do so, there is a mistake, I don't need this term. I don't need this term. Okay. There is a mistake. This term I do not need. Okay. So directly I'm taking connect to disturbance. Actually, this will go there. देखिए একটু adjust করতে পারি. Yes. This will be like this. Okay, so whole square of this entire thing, 1 by summation xi square whole square of this thing, expectation we are operating inside. So expectation of ui square, and here also I need to write one expectation. Wait, let me check if I can do this thing. Yes, I think it's fine now. So whole square of this term, summation xi square, expectation of ui square, summation xi xj, expectation of ui uj. Okay. Now expectation of ui uj is equal to 0 because still we are considering the non-autocorrelation assumption. However, expectation of ui square is sigma I square. So summation xi square, sigma I square, and this whole square term is there. Okay, so as I mentioned in this slide, it will come like this. We are exactly getting that. We are exactly getting that when we are considering variance of beta hat OLS. Okay, so it is not similar to that of the best linear unbiased estimator or the property of the best linear unbiased estimator we got in context of ordinary least square or in presence of homoscedasticity. Okay, and as we are not getting this thing, already we proved that when we discussed the properties of OLS estimator, etc., we proved that we can have a series of unbiased estimators. However, if I consider any other alternative, among these alternative estimators, unbiased estimators, the exact form of the beta hat OLS or exact form of the variance of beta hat OLS gives us the minimum. Okay, so when we are not getting the exact form, that is sigma square divided by summation xi square, we can argue that since this is not giving the variance of the OLS estimator, it is giving something else, it is not the minimum variance. Okay, so we are getting the unbiased estimator in presence of heteroscedasticity. However, we are not getting the best estimator. Minimum variance property is disturbed. So we can sum up OLS still unbiased and consistent under heteroscedasticity. Heteroscedasticity invalidates variance formula for OLS estimator. Okay, sorry. Variance formula for OLS estimator, and thus OLS is no longer the best linear unbiased estimator. There may be more efficient linear estimators. We need to check that thing. Interpretation of R square is not changed. That is, the interpretation of goodness of fit will not change. It will still remain ESS by TSS. The usual t-tests are not valid under heteroscedasticity because, the variance is not minimum. When we consider t-statistic, it is beta hat divided by standard error of beta hat. So as long as we cannot ensure this variance of beta hat is the minimum or the standard error of beta hat is the minimum, if we estimate the t-statistics, that will give us erroneous results. That will not give us the right results. Okay, so what we are finding, no problem with the unbiasedness, no problem with the goodness of fit analysis. However, there is a problem with respect to the minimum variance property, and therefore there is a problem with respect to the usual t-test. Okay, so these are the issues arising in presence of heteroscedasticity. Any question up to this? From the consequence part. Any question? Is it?
ম্যাম
Yes, Lakshadip.
ম্যাম বলছি ভেরিয়েন্স অফ বিটা হ্যাট ওএলএসটা মিনিমাম নয় কেন একবার বলবেন?
Since it is something different from sigma square divided by summation xi square. Already
ও আচ্ছা
that for a little bit change in the estimator, we do not get the minimum variance property. Okay, when we discussed the standard steps of the OLS, I hope you can remember we did a long exercise, considering another unbiased estimator. Okay, however,
ইয়েস ইয়েস ম্যাম
did not get the minimum variance property. Following the same logic, same reason, this problem, will arise. Later we will, when you will learn about the WLS technique, weighted least square technique in case of, or in context of heteroscedasticity, using the Cauchy-Schwarz inequality, I'll prove one thing as well. At this moment, since it is not something different from the variance of the OLS estimator, it is not the minimum variance. This is the idea. Any other question, anything on consequence? Okay, so I'm moving back. Now, detection of heteroscedasticity, we will get a raw data on yi and xi. Whenever you will go for any kind of empirical investigation, empirical research, you will get only a raw data on xi, yi. So, looking at the data, you will not understand anything. So, we have to understand what can be the detection method of heteroscedasticity. Because if there is heteroscedasticity, and if you apply the OLS technique, all of your results will be the wrong results, okay? The standard mechanism, if you consider the graphical method, the standard mechanism is plot UI hat square, that means RSS. Not RSS, this is the squared of the residual, rather. Squared of the residual. UI hat is the equivalent to EI, which is residual. I'm considering the squared values. Squared values we are considering because we want to find out or we want to do this on the basis of the absolute values. We are not interested about the direction of the residual. We are interested about the absolute values of the residuals. So, graphically, if we like to check this thing, we can plot EI square or UI hat square against XI. If there is some kind of pattern in the graph, if it is not, like any general scatter, in that case, we can have a guess that the data may have the heteroscedasticity problem. Here you are getting a pattern, you are getting a pattern between EI square and XI in all the graphs. Okay, so if this happens, you can have some idea that there may be heteroscedasticity. However, you should remember always the formal test is required. Formal test is the right thing to do. Another problem with the graphical analysis is that here you can consider one explanatory variable at a time. So your model may have 10, 12 explanatory variables, So in that case, with each of the variable, you have to do this separately. It cannot address all the explanatory variables simultaneously. Okay. So always this is the limitation of any kind of graphical plot. You can consider 2 factors at a time. Okay. Now to understand the matter more clearly, I have taken a piece from Madala. Okay, Madala's book is with you. So, I hope all of you will be able to go through all these things. Okay, and it is very lucidly written, so it will help you a lot. Okay, so from Madala, I'm considering table 5.1. It is the data on consumption expenditure, that is the Y variable, and the income, that is the X variable. We have observations on 20 families. So Y is the consumption expenditure, okay, in thousands dollars, and X is the income in thousands dollars. Okay, so these are the 20 observations. Once we get these 20 observations, we can estimate a regression model. And from that estimation part, we can generate the residuals. If I consider yi minus yi hat, once we do estimation, we will be able to generate yi hat. And from yi minus yi hat, we will get all these residuals, In your practical class, I hope all of you did all this kind of exercise. Given the data on Y and X, how we can calculate these residuals. Am I right? You did all these things in your practical? Yes or no? Did you do regression in your practical session?
Yes, ma'am.
And you did all these things? You know how to find out the residuals? কি এক্সেলে তো তোমরা এটা করেছো, তোমরা জানো কি জানো না সেটা বলো। কি আরাত্রিক, রাজদীপ, এগুলো তোমরা শিখেছো?
Yes, ma'am. এগুলো আমরা করেছি।
এগুলো সব প্র্যাকটিক্যালে হয়েছে তো? মানে এরপরে তো তোমাদের প্র্যাকটিক্যাল এক্সাম হবে, এই সবগুলোর উপরই তো আমি কোয়েশ্চেন দেব না। For that matter, I'm asking যে whether you know all these things or not.
Yes, ma'am. We've been doing this class.
বাকিরা, শ্রেয়া, করেছো এটা? রাজদীপ?
Yes, ma'am.
So you know all these things. Because, as we move on, all the issues, we cover in the practical session so that we can combine the matter and understand the thing very well. So you know how to calculate the residual. Actually, you are just clicking on a box and that will generate the residual, yi minus yi hat. That will generate the residual. Okay. So from this 5.1, we can have 5.2. Okay. Now, once we get this table 5.2, and if I order all these X values, here I have arranged, or Madala, has arranged all the observations in increasing order. Okay. Here the observations were like, 22.3, 32.3, 36, then 12. And here you will find the sequence has changed because X has been arranged following the increasing order of magnitude. So if we rearrange the x values in increasing order of magnitude and put the relevant residuals beside this, we are getting, as the x value is increasing, the residual value is also increasing. Sometimes there may be some fall, However, under most of the circumstances, as x value is increasing, residual is increasing. So there is a pattern. There is a pattern between x and residual. So this is the graph. This is the relevant graph. So as the x value is increasing, we are getting the residual value in general is increasing. Sometimes there may be some drops. However, this is the general pattern. In the negative value, if you plot the negative values, you will get this thing. Okay. So from this table or using this table, also practice the thing using your Excel. Not only the theory, but also the Excel. Okay. You have these database with you. Just type all these observations, then estimate the regression, then find out the residuals, then arrange x in increasing order, put the relevant residuals beside, and then plot the residuals against the x values, or residual square against the x values. Okay. So you will get this kind of plot. Okay. So not only theoretically you will do this thing, but also practice this thing using Excel too, so that the things will become very interesting to all of you and you will learn the matter very well. Okay. So this is the estimated value regression, So, in Excel, if you do this thing, you may check whether you are getting these values, these standard errors, these R squared, these RSS, all the things you will be able to check. This is a small database and easily you will be able to type all this matter. Okay, so all these things are there and therefore, from this database, if I plot the things, I'm getting an evidence of heteroscedasticity. Okay. Now a rule of thumb is suggested sometimes, that is, if we consider the logarithmic transformation of y and x, under many circumstances, we find that the heteroscedasticity issue is removed. This is only a rule of thumb. Okay, take logarithmic transformation of y and x and run the regression. Why this is only the rule of thumb? Because, when you are considering the logarithmic transformation, your interpretation of regression coefficient is changing. Now it is the elasticity, d log y by d log x, that is nothing but elasticity. In the original regression, it was change in y due to change in x. However, when we are moving to this logarithmic transformation, it is becoming the elasticity. The idea is becoming the elasticity. Okay. So always we do not need, or always it will be not right to work with the elasticity interpretation. Okay. So it is only the rule of thumb. However, we need to learn more formal method by which we will be able to detect heteroscedasticity and by which we will be able to, remove heteroscedasticity. Okay. So formally, we need to handle both the issues. So there is, in Madala, you will get this table too, when they are considering the logarithmic transformation and running the regression, arranging the x or log x in increasing order, then no pattern is revealed. There is no, now if we arrange the residuals accordingly, we are getting no pattern. So I'll request all of you to do this exercise too using your Excel. So start with the original data, run the regression, then arrange x values according to increasing order of magnitude, then you plot the graph, then next you consider the logarithmic transformation of y and x and check whether now you are getting only the random scatter or random values of the residual, not something which is giving you the pattern. Okay. So as I mentioned, this is only the rule of thumb. Graph is also limited. We have to go for several formal methods of detecting heteroscedasticity too. Now, for all the tests of heteroscedasticity, the null hypothesis will be no heteroscedasticity. As in the beginning I mentioned, in the entire regression analysis, we consider zero parameter type hypothesis. When we consider or when we try to check significance of the coefficient or try to check whether there is interrelation between y and x, we consider zero parameter type hypothesis. That is no relation, no explanatory capacity. So here we consider the no kind of hypothesis. So in presence of heteroscedasticity, autocorrelation, if we need to check, whether there is heteroscedasticity, whether there is autocorrelation, again the null hypothesis will be no heteroscedasticity, no autocorrelation kind of thing. So H0 is no heteroscedasticity. So initially we are starting with a regression model, say yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. You can consider it in a two variable case as well. The standard practice is, generally we present all these things in presence of a number of explanatory variables. However, you can reduce the number of variables, you can consider single variable, etc. Okay. So the general context has been presented. Step 1, do OLS to obtain the residuals. Always this will be the thing. In case of graphical analysis, this will be the standard practice. In case of most of the formal methods, you have to start with finding the residuals. Okay, ui hat. Step 2, run the following model with the covariates and their cross products. So what I am doing, I am again considering the square of the residual. In case of graph, I considered square of the residual. In this case too, I am considering the square of the residual. There is a typo. This will be ui hat I, not 1. Okay, this should be I. There is a typo. Okay, so ui hat square is equal to alpha 1 plus alpha 2 x2i plus alpha 3 x3i plus alpha 4. Then I am taking square of this, x2i square, alpha 5 x3i square. Then I am taking cross products, alpha 6 x2i x3i plus error. So what I am taking, whatever explanatory variables I have in this new regression, that is when I am considering the square of the residual, I am regressing square of the residual on those explanatory variables, their squares, their cross products. I am repeating. I am regressing the square of the residual on all explanatory variables present in the original model. This is the second regression. Don't mix up this regression model with the first one. This is the original one, on the basis of which we derive the residual. Once we get residual, I am taking square of that residual and running a new regression model. In this new regression model, I am considering all the explanatory variables, their squares, their cross product, and there is the random error vi2. And then derive R square. From this model, we derive the goodness of fit, R square, ESS by TSS. Now, NR square follows the chi-square distribution with k minus 1 degrees of freedom, where k is the number of unknown parameters in step 2. Because this is the regression on the basis of which we are going to test heteroscedasticity or presence of heteroscedasticity. So if we find that this chi-square, the estimated chi-square is greater than the critical chi-square, that is one which has been found on the basis of the tabular value of the chi-square. If the estimated chi-square is greater than the tabular value, you have to reject H0. This is the standard rule. Estimated value, if it is greater than the tabular value, we reject H0. Rejection of H0 means there is heteroscedasticity. Okay, so I'm repeating the steps. Standard regression model, find out EI, take square of that, then fit a new regression model on all explanatory variables, their squares, their cross product, calculate R square. And then we have to consider the chi-square. If this chi-square, that is overall significance of the model. Overall significance of the model. This chi-square will give us overall significance of the model because R square is the measure of goodness of fit. So, you got some idea, when you consider the ratio of R square kind of model, R square by 1 minus R square, in the hypothesis testing part, you got the F statistic. So actually that was the ratio of two chi-square. Therefore, you got the F statistic. Here I am considering a single R square, not the ratio of two R square kind of thing. So it will be chi-square. Okay. So ESS by TSS, that follows chi-square distribution. So if the estimated chi-square, is greater than n into R square, just simply you have to calculate n into R square. That n into R square is following the chi-square distribution. So if that is greater than the critical value, tabular value, reject H0. So here I have given an example. It is in terms of logarithmic values of the variables. So in the estimated equation, log of the explanatory variables, in the form we originally had in the original model, their squares, their cross product, calculating R square. Okay, so here it will be your homework to find out n into R square and test or conclude whether there is heteroscedasticity or not.
ম্যাম
Yes.
ম্যাম বলছিলাম যে একটা স্লাইডে যেতে পারছেন, ওই গ্রাফের স্লাইডটা, মানে ডেটাগুলোর আগে গ্রাফের ওই স্লাইডটা যেতে পারবেন একবার?
What do you want to know? Dorpak, what is your question?
ওইখানেতে একটা জিনিস ওই বুঝতে পারিনি, ওই গ্রাফের স্লাইডটাতে।
This one? This one?
হ্যাঁ ম্যাম, হ্যাঁ এখানেতে এই সব পয়েন্টগুলো যেটা রেসিডুয়াল গুলো দেখাচ্ছে, ওটা ম্যাম নেগেটিভ রেসিডুয়াল, মানে অনেকটা মানে মানে নেগেটিভ পজিটিভ রেসিডুয়ালের কোনো মানে মিনিং আছে আলাদা করে?
No. Whatever you got, you are plotting those things. That's all.
আচ্ছা আচ্ছা আচ্ছা।
Okay. There are similar kind of tests, One is Anscombe and Ramsey test, which we call the reset. This is also from Madala. It will be easier for you to, do these things from Madala. Therefore, Ramsey test. In this case, instead of regressing UI hat square on Xi's, they suggested run the regression where UI hat will be regressed on y1 hat square, y1 hat cube, etc. Okay, so they are calculating y hat values and then they are taking square, cube, etc. and regressing UI hat, that is the residual on yi hat square, yi hat cube, etc. Okay, so this is another procedure. Glaser test is very interesting. In case of Glaser test, Glaser is suggesting consider the absolute value of the residuals, mod value of the residual, and regress it on 1 upon xi, root over xi, 1 upon xi, and root over xi. You will find that residual on xi, residual on absolute value of residual on 1 upon xi, absolute value of residual on xi hat, run all these models. If one of these three models indicate heteroscedasticity, in that case, you have to go with heteroscedasticity. If all the models suggest homoscedasticity, in that case, the situation is homoscedastic or variance of UI is homoscedastic. You know, for rest of the cases, that is 2 of the cases are showing heteroscedasticity, 1 is not, or all 3 cases are showing heteroscedasticity. In all these cases, all other possibilities, you have to consider heteroscedasticity of the error term. Okay. So, using the table, you have run this Glaser test as well for your practical things. Run the Glaser test as well. Okay. You will get interesting results. The results will be like this, based on table 5.1, 5.2, if you run all these things using Excel, you will get all these results. These are the 3 estimated regression, x, root x, and 1 upon x. In all the cases, you are considering the modulus value of the residual, and that you are regressing on x, root x, 1 upon x. Okay. So, if you look at the standard error and the coefficient value, if you divide this by this, the t statistic will be very high in all 3 cases. T statistic will be very high in all 3 cases. High t values indicate rejection of null hypothesis. High t values means, residual is related to x. Residual is related to root x. Residual is related to 1 upon x. So, there is some relationship between the x, root x, 1 upon x with these residual. Hence, you have to reject null hypothesis of no heteroscedasticity. Okay. And all these 3 models are good, Now, for these 3 variants, for the future task, what you will select, which one you will finally select, that will depend on these R squares. That will depend on this R square. Here, for the first model, R square is very high. So, among these 3 pattern of relationship, you can go with the first one. That is the absolute value of the residual is a function of x. If the second gives you the highest R square, in that case, the absolute value of residual is related to root x and so on. So, once you estimate 3 models, if you find that only one model is showing heteroscedasticity, go with that pattern. If you find 2 models are showing heteroscedasticity, check or compare R square. If all the 3 models show heteroscedasticity, then again you have to check R square. I am repeating. If a single model shows heteroscedasticity, you have to select that one. Okay, heteroscedasticity is there and this kind of relationship is there between the residual and x. If more models show heteroscedasticity, in that case, check goodness of fit to select the final form of relationship between the residual and x. Okay, any kind of relationship between x and residual is indicating heteroscedasticity. And how we are understanding the relation, looking at the t values, coefficient divided by standard error, coefficient divided by standard error, coefficient divided by standard error. Okay. Should I proceed more, or for 1 week you will be able to complete up to Glaser test, or I'll cover one more? What will be your opinion? Should I explain one more test?
Ma'am, can I say something if everyone's okay with that?
Yes, why not?
ম্যাম বেসিক্যালি বলছি যে মানে আমাদের ধরুন এখানে না বারবার করে একবার করে কারেন্ট থাকছে, একবার করে কারেন্ট চলে যাচ্ছে, আর মানে এরকম একটা সাইক্লোনের একটা ব্যাপার আছে। তো তো যদি আজকের ক্লাসে এতটা অব্দি থাকে আর এই উইকে আমরা এটা মানে বেসিক্যালি পড়ার চেষ্টা করি, would that be okay?
Yes, that I'm asking for. Because what I'm telling, do the theory, do the practical. Okay, so in that case, I'll shift to the likelihood, MLE kind of thing, etc., which actually I covered earlier, which I sent you earlier. That therefore I'm asking, coming to this juncture, should I cover one more test or detection method, or should I stop here?
Oh, ma'am, that is only what I was saying. Like, can we stop here for today if everyone's okay with that?
ইয়েস ম্যাম, এখানে স্টপ করলে বেটার হয়।
Okay. Bakira, Oishi and Shreya.
Ma'am, এই অবধি থাক।
No problem. I have no problem. For that matter, only I just asked you, coming up to this. Because, and I'll expect that all of you will go through the consequences and up to these, not only the theory, do the theory and the practical, so that you learn the things very well. This is the only thing for which we are keeping practical with this course, so that you can practice the things twice, the theory and the thing, whether you are getting the results which we are showing, etc. Okay, and already the practical exam is due, so, and as per my knowledge, you did all these things, so again, when you are learning the theory, sometimes what happens when you are doing the practical, not learning the theory that well, it becomes difficult to grasp the matter. So once you are learning the theory part, again go back and do the similar kind of practical exercises, and whatever difficulties you are facing, you can ask it to Pravesh, you can ask it to me, so that we can bridge the gap. We can bridge all kinds of gaps. Okay, so in terms of heteroscedasticity, I'm stopping here and I'm moving to MLE. Okay, as per my knowledge, most of the students understood the maximum likelihood estimation technique. Only a few students mentioned that, there may be some problem regarding this part or that part. So I am just telling you the entire thing. After that, if you have any question, please ask me. So this is the standard regression model. Sometimes what happens, we consider the large sample. Okay. So, and we need to apply the techniques which are related to the large sample. The finite sample will not work for my research purpose, and I have to go for a large sample. Now, if I have a large sample, and to begin with, we have knowledge about the distribution of the error term, we will be able to apply the iterative technique, that is the maximum likelihood estimation technique, to estimate the parameters of the regression model, derive the value of the sigma squared 2. So all these things are possible. The main difference between the OLS technique and MLE is that here we need a large sample, number one. And number two, here to begin with, we need the knowledge of the distribution of the error term. In case of the least square technique, as you know, the distributional aspect is not required up to estimation. That is required only when we are going for the hypothesis testing. By the way, during the viva or discussion, whatever you say, many of you mentioned that, Ore Baba, hypothesis ta hoyni, I'll be not able to do that. So now you have to come out from that situation, because you need to learn the hypothesis testing. Some of you promise that you will go back to your statistics notes and first you will revise those things and then you will come back and you will learn all these things. So side by side, please start doing all these things. Don't keep all these things for the last day. Okay? Because always in that case, there will be a panic in your mind. So if you have any question, any query regarding the standard hypothesis testing, that also we can clear during the class or having some special session. Okay, so don't keep it aside. Please go through all these things. Okay, so yi is the independent variable, xi is the dependent variable. So this implies yi. If ui is normally distributed with mean 0 and variance sigma square, that implies yi. That yi's are also independently and normally distributed because ui is randomizing yi. What will be the nature of yi? That will depend on the nature of ui. Okay. So if ui is normally distributed, yi will be also normally distributed. The mean, y bar, under many circumstances you calculate it, y bar will be alpha plus beta x bar. And the variance of yi will be that of the variance of ui because ui is randomizing yi. So variability of yi will fully depend on variability of ui. So variance will be sigma square, whereas mean will be alpha plus beta xi. Okay. Or in other words, if you consider expectation of yi is equal to alpha plus beta xi. I'm considering xi to be non-stochastic. Expectation of ui is equal to 0. So expectation of yi is equal to alpha plus beta xi. Now I have to consider the joint density function because there are n observations here. The joint density function is equal to product, capital pi. I is equal to 1 to n. Then I am writing the usual normal distribution. 1 by sigma root over 2 pi. That I am writing as 1 by 2 pi sigma square whole to the power half. So I am writing 1 by sigma root over 2 pi e to the power minus 1 by 2 sigma square because I am telling the variance is sigma square. Then xi minus mu, that I am changing to yi minus alpha minus beta xi. This alpha plus beta xi is the mean. So yi minus y bar I am considering, or yi minus expectation of yi I am considering. Okay. So product I is equal to 1 to n, 1 by sigma root over 2 pi e to the power minus 1 by 2 sigma square yi minus expectation of yi whole square. This will be the joint density function. Okay. So since I am in the next page, therefore I mentioned the joint density function once again. And from there, I'm writing the likelihood function. This joint, from the joint density function, we are moving to the likelihood function. Structurally, the joint density function and the likelihood function will look alike. Okay. So L, now likelihood function will be the function of parameters. Here the parameters are alpha, beta, sigma square. So L is a function of alpha, beta, sigma square. This is the difference between F and L. F is a function of variables, whereas L is a function of parameters. Okay. So look at the joint density function, the definition of the joint density function and the likelihood function, which we covered in the statistics course. You will find all these things. F will be the function of variables given the parameters. L will be the function of parameters given yi's. However, the right-hand side will remain same. Then I am considering the logarithmic transformation because here there is e to the power something and taking derivative will be difficult. So I am considering the logarithmic transformation. So from product, when I am taking the log version, I am going to the sum version. So I am getting minus n by 2 log 2 pi I'm keeping log 2 pi separate from log sigma u square, because when I'll take the derivative, I have to take derivative with respect to alpha, beta, and sigma square. So I'm keeping 2 pi parts separate so that my work becomes easier. So, from this term, I'm getting two terms. And from this term, minus 1 by 2 sigma square, sum of yi minus alpha minus beta xi log e. So it is simply this. So when I'm taking logarithmic transformation, it reduces to this. So first you have to practice up to these. You need to know what will be the log L. Once you get log L, then or easily you will be able to take differentiation. Three first order conditions you need to consider, because you have to maximize log L. So you have to consider three first order conditions. One with respect to alpha, another with respect to beta, and another with respect to sigma u square. Okay, so d log L by d alpha, take the derivative, set the first order condition, find the value. D log L by d beta, take the derivative, set it equal to 0, find beta hat. D log L by d sigma u you can do, d sigma u square you can do. Whatever you like you can do, you will get the same result. Okay. So sigma u square also you need to find out. Now if you look at the alpha hat value, it is y bar minus beta hat x bar, which is similar to that of the OLS value. Using the least square technique, you get this value. So it is similar. Beta hat summation xi yi minus nx bar y bar divided by summation xi square minus nx bar square, similar, no difference. When you are finding the sigma u square value, there is a difference. In case of OLS, the value was RSS by degrees of freedom. In case of two variable analysis, it was RSS by n minus 2. If you consider a general k variable analysis, it will be RSS by n minus k degrees of freedom, However, here you are getting n, all observations you are getting. You are not getting n minus 2 or n minus k, whatever. Now it is a large sample. MLE we are applying or we can apply when there is large sample. Now when you are considering a large sample, taking difference of 3 or 50 from number of observation does not matter, because n is moving towards infinity. N is very, very large. So from that large observation, if you have 50 parameters in your model, minus 50, 3, 4, 5, 6 does not matter. So when we consider the large sample in calculation of SU square, what we find, the n minus k or the degrees of freedom in the denominator has been replaced by n. Okay, so this is the difference in terms of estimators. Alpha hat, beta hat, all these things are identically equivalent between the two techniques. However, there is a small difference when we are considering the sigma u square value. So this is all about the maximum likelihood estimation part that you need to cover in this semester. Any question? Anyone, any question? Is it okay?
Yes, ma'am.
Some students mentioned before the exam that there are some problems, for 1 or 2 points. So for those students, I'm asking, are the points okay, fine at this moment?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. Very good. Now you have to do the steps. Steps are with you. You do the steps on your own, take the derivatives on your own, then check whether you are getting these results or not. Things will be very, very clear to all of you. And the last thing, where you had some questions, that is the prediction part. That also I gave you before the exam, the prediction kind of thing. And now a lot and lots of prediction are going on regarding the different waves of COVID, how the disease will spread. Now regarding the yash, what will be the direction of the air, what will be the nature of weather, how much rainfall will be there. So all this kind of predictions are moving around us. All predictions and forecasting moving around us. Okay. So the main difference between the prediction and the standard regression analysis is here, for a given series of values of X, we have to find out the Y. Given X is equal to X naught, given these factors, what will be the pattern of Y? So that we need to find out. Now, in case of general regression, both YI and XI, for both YI and XI, we get the observations, varying observation. Here, for XI, we are not getting the varying observations. Rather, we are getting a specific value. Given the specific value, what will happen regarding YI, that we have to consider. Okay, so given the fact that for the last few cyclones, when the speed of air was like this, what will be the nature of this particular storm, or what will be the nature of this particular cyclone? Okay, given the fact that for this depth of clouds, this was the amount of rainfall, what will be the volume of rainfall from this particular time? Okay, so all these things are happening around us, okay, at this moment. So it is just that. Prediction is just that. So predict the value of Y corresponding to given value of X is equal to X naught. X is not varying here. Okay, so there are two types of predictions, point prediction, interval prediction. In case of point prediction, you have to find a specific value of Y naught. In case of interval, you have to set an interval for this Y naught, So this will be the thing. So, the point prediction is given by the regression value corresponding to X naught. This is given by equation number 1. The true value is like this. In the true factor, there is the randomness. Exactly, we do not know what will be the speed of cyclone when speed of cyclone in Kolkata. Okay, so there is randomness in the factor. Okay, and for that matter, everybody is telling it is our forecast. It is our prediction. Nobody is telling exactly this will happen. Okay, because in the true value, there is the randomness. There is some error. Nobody knows how the air will pass, how the wind will pass. Nobody knows. So only we are predicting given this few knowledge, given these factors. Okay. In equation number 1, it is a very simple construct. Therefore, I am considering a single fixed X value. When really or practically we are doing this, there are a series of X for which we have some specific values. Okay. So there is a combination of X for which we are predicting this. Okay. The thing is more complex. It is not that simple. However, we can have some idea in our age of 19, 20, So most of you may be 19 or 20. So during this age, so you can have some idea about this. In future, when you will be older, you will do the complicated models, complex model. Okay. So the true model is equation number 2. The predicted model is equation number 1. So there will be some error between the two. So we are trying to capture that error, prediction error. This is not the residual as such. This we call the prediction error. So prediction error is the gap between the random Y naught and the predicted Y naught. I'm not telling it estimated, rather we are telling it predicted. So, if you just take the difference between Y naught and Y naught hat, you will get this equation number 3. So your 1 and 2 are there, and if you take the difference, you will get equation number 3. You can discuss something about the nature of this prediction error. nature we generally discuss, or we are interested about two natures, central tendency and the dispersion. So for that matter, I'm considering expectation of E naught, calculating expectation of this equation number 3. Now, if I consider the expectation, it is expectation of U naught plus, or sorry, minus expectation of this minus expectation of this. Okay. Now, expectation of U naught by classical error term, it is a random classical error, 0. Expectation of alpha hat minus alpha, you know, if you operate expectation inside, expectation of alpha hat is alpha hat minus, sorry, expectation of alpha hat is equal to alpha minus expectation of alpha is alpha. So alpha minus alpha is equal to 0. If you bring expectation inside, expectation of beta hat is equal to beta, because alpha hat, beta hat, these are the unbiased estimators of alpha and beta. Okay. So, you know, beta minus beta will be equal to 0. So expected value of the prediction error is equal to 0. One point I should mention here, all this prediction and forecasting, etc., these are the post-regression analysis. So we have alpha hat, beta hat, these things in our hand. Remember, this is post-regression analysis, okay? Otherwise, you may have some question from where we are getting this alpha hat, beta hat, etc. Already, a regression analysis is in our hand. This proves that prediction given by equation 1 is unbiased, or more specifically, y naught hat is a linear unbiased predictor of y naught. Next, we calculate the variance of E naught, which will be equal to variance of E naught square. And we are getting, you know, E naught is basically this. So we will get variance of U naught plus variance of these plus variance of these. Then covariance between U naught and these and this and these and this. Okay. So 3 covariance terms will be there along with 3 variance terms. So these are the 3 variance terms, you know. Variance of U naught plus variance of alpha hat plus x naught square variance of beta hat. Okay. Now there are 3 covariances as I mentioned. However, I have written only one here because the other 2 covariances, which are between U and alpha, U and beta, these covariances are absolutely equal to 0. So this has been written here, you know. Expectation of alpha hat minus alpha whole square, which I got from this model, you know, when I am taking the variance part. This is the variance of alpha hat, expectation of beta hat minus beta whole square, that is the variance of beta hat, expectation of U naught square, that is the variance of U naught. So all these things are there. By assumption, U naught is independent of U1, U2 to UN, because this is the error of the true model. So it is, this is the error of the predicted model. This is the error of the test. You know. So this is the error of this model, this particular model, when x naught is there. And alpha hat, beta hat, that has been calculated on the basis of a standard regression model. Yi is equal to alpha plus beta xi plus ui. So alpha and beta has been calculated on the basis of that model. Okay, so U naught is independent of all UIs, and thus it has 0 covariance with alpha hat minus alpha and beta hat minus beta. So the 2 other covariances are equal to 0. So these are the 2 properties of E naught, expectation of E naught and variance of E naught. Okay, once we understand this thing, in the next step, I have just treated the values you already know. Variance of alpha hat you know, variance of beta hat you know, covariance alpha hat beta hat formula you know. So just I am putting the formula, variance of U when we are considering homoscedasticity, that is sigma U square. So I am putting these values and calculating the final form of the variance. Okay. So I think I'll stop here. because you check up to these for the prediction part. The rest of the things, because for the rest of the things, I have to bring the distributional aspect. I have to mention about the interval, etc. That will be, maybe too much for you. So I'm stopping here. So look at the basics of prediction from any book. Why we predict, what does it mean? From any text you can check. And then how in a regression analysis I'll put it, how I'll consider the prediction error, what are the nature of prediction error, up to this I covered. Rest I'll cover in the next class along with heteroscedasticity. Any question up to this? Anyone, any question up to this? You can do it from Stock and Watson, you can do it from Madala. Both the books are more or less will be, easy for all of you. The basics, the steps are there in the slide. Anyone, any question?